for giving the opportunity. Am I
Thank you,
audible?
sir. Yes. Thank you, sir.
Yes.
It's pleasure is all mine. Thank you.
Yes. So can I share my PPT?
Sure, sir. Please, and it would be great if you can open up your webcam also, so that it would be more
Yes,
interactive in that case.
Yes, sure.
Thank you.
I'll just open it. First, let me share my PPT, then I'll open it.
And again, I would also like to request with every participant to actively take participate into the discussion into the webinar, so that it can be more engaging and knowledge exchange session. All right. So now platform is
Yeah.
yours,
So
Dr. Harsh.
yes, thank you very much, Dr. Akshay Gupta. So first, let me introduce myself to all of you, and good evening to all of you. I am Dr. Harsh Tripathi, Assistant Professor, Symbiosis International DMD University, Pune. My research area is basically statistical quality control, and the pillar of statistical quality control is acceptance sampling inspection plan, control chart, and process capability indices. Moreover, this I explored probability distribution theory area also. Where the major concern with the probability distribution is the estimation and the properties of the probability distribution. So one of my paper which is published, I think 3 years back or I think 2.5 years back. This is exponentiated X gamma distribution, a monotone failure rate model, and its application to lifetime data. So this is the title of today's talk, and I am very joyful to share this paper with all of you, insights of this paper with all of you, so that if any one of you understand those things or discuss with these things in a more detail, any one of you contact me via research collab lab, scholar lab basically, or I can share my email also if scholars lab platform permit this. So today's title is exponentiated X gamma distribution, a monotone failure rate model and its application to lifetime data. So initially, the thought behind to develop this paper is that there are so many distributions, and the common distributions, known common distributions, those are exponential, Bevel, gamma, normal, and logistic. These are the very much known distributions which is used by the many researchers in their uh, significant contribution. So, and apart from this, in the literature, there are so many families are available so that you can extend any of distribution to the certain uh, good extension with the number of parameters increased. So this is the motivation because it is not possible to judge every situation, real life situation, or model every real life situation with the known Bevel, exponential, normal, logistic distribution. There may be some other distributions. So there are so many distributions on available in the literature, and recently in last decade, researchers are very much keen to develop these models. And moreover, this they are developing the properties, statistical properties, estimation also, because the all the things which we are doing in the probability distribution, we are just doing the modeling of the real life scenario, and our interest is to determine the estimate of the parameter. This is just a whole thing which we can do with the parametric inference, and to estimate and to check the whether estimator is good or not, there are certain properties. So this is how the thought comes in our mind. Me and with and my collaborators also thought that it is good to extend X gamma distribution. So the X gamma distribution basically developed by Sen et al. In 2016, and this is one parameter distribution. So to extend this one parameter distribution to the two parameter distribution, we use exponentiated family. We use exponentiated technique to extend this distribution with the two parameter. So this is the initial thought we have regarding the same. And the research gap, we found that there is no such work is available in the literature, and there is no such work available regarding the estimation of the parameter in the literature. So we are interested because X gamma is very much, we can say, good distribution contributed by Sen et al. Because it is a mixture of exponential and gamma distribution. So it has some good properties so that we can model real life situation in a very much possible way. So this is the basic thought behind this introduction and motivation which I have discussed with you. So exponential x gamma distribution is two parameter distribution. Now the mathematical foundation which associated with the any kind of distribution is that the development of or the mathematical formulation of probability density function and cumulative distribution function. So first equation which you see in this one, this is the one parameter x gamma distribution probability density function which we have written fx comma theta, basically theta square upon 1 plus theta, 1 plus theta by 2 x square e to power minus theta x. This is the one parameter distribution. Now we use exponential family and termed as the exponentiated x gamma distribution, which is nothing but this power of the CDF of the x gamma distribution, which we have written in the following equations. These two following equations, which you can see easily, the capital Fx and small fx, with this two parameter alpha gamma theta. These are the equation of exponentiated x gamma distribution with the CDF capital Fx and PDF small fx. Now the things are started because the probability distribution, any probability distribution associated with these two things, cumulative distribution function and probability density function. Based on these, we can estimate the survival function, we can estimate the hazard rate function, and to judge whether this is a good probability distribution for our chosen data set, so that we can apply or we can estimate the parameter by using this a new developed distribution. So for this we just have gone through and some properties also, but here we have mentioned, we have plotted this density function plot of the exponentiated x gamma distribution for different choices of alpha and theta. Alpha is the parameter which is exponentiated one, and theta is the already chosen with the x gamma distribution. So there are, I think, six or five combination which we plotted the density function. We found that this is very much positive skewed. This can be applied to the data where we have positive skewed data. So this is first filter we apply to judge whether we can go with this distribution or not. So this is kind of situation where we can apply. Now, in this paper, what we did, we actually derived several properties like mean, correct, moment generative function, hazard rate function, and survival function, order statistics, and Boniferini Lorentz curve also. So these kind of characteristics we apply, sorry, we derived. So we found that regarding the hazard rate function, the distribution has increasing failure rate and decreasing failure rate, and also bathtub shaped hazard rate function with certain range of the parameter which is we have chosen with alpha and theta in our distribution, proposed distribution, exponentiated x gamma distribution. So it has all these three kind of situations which coincide with the real life situations with certain range of the parameter. Already I have mentioned here, and if anyone is interested in this, then they can go to the published paper and they can read it out. It is almost 30-35 page, I think, paper. So they can read it out also in detail. And here survival function is also one of the tool to see what is the survival of a product after a certain time. So these are the properties which we have uh, derived, and moreover this hazard rate function is the very much important to judge the pattern whether we can go with this distribution or not for the R chosen data set. So that this equation which is given here, S, this is capital S, basically survival function of the exponentiated x gamma distribution. Now these are the properties which I have been talking: the raw movement, generating function, mean deviation, quartile function, and all these are the key properties which you can use anywhere if you are applying this distribution. And these are the important ones because to judge whether it is positive skewed, negative skewed, to judge whether the mean is greater than median or mode, mean is less than the median mode, to determine the Lorentz one Ferrani curve, to determine the if it is not possible to use this raw movement or derive the raw movement in explicit form, then you can use generative function also to generate the movements, or to determine the probability distribution of the sum of the random variables. So these are the important ones which is associated with the statistical distribution, probability distribution. So these are properties which we have derived, and this is the key mathematical result regarding the rth movement, which you can see expectation x to the power r and alpha theta square upon 1 plus theta bracket k1 and plus theta by 2 k2, where k1 k2 is not the explicit function. This is the function of alpha theta and movement r, basically rth movement. If it is, then we have written this what is actually k1 k2. So this is k1 k2 is here. If you apply this distribution, then you should replace theta with the estimated value, alpha with the estimated value, r with the some movement. If you want second one, then r with 2, and you just calculate this. And one question maybe comes in your mind, that how can we calculate this summation series? So for this, nowadays this is very much easy. You can use R, Python, anything else, Mathematica, MATLAB, anything which you want to wish, or which you wish to apply or to derive or to compute any value of the mathematical result of the probability distribution, because it is not possible every time every distribution has certain explicit form like exponential gamma. It is not possible. It is not possible like explicit form like binomial, Poisson, negative binomial. It is not possible. So we have to go with this some computational tools. I I did this computation with the R, basically. I used R, and anyone go with the Python also, MATLAB and Mathematica. So this is how, and this is the picture of the survival function. So this is just nothing, the 1 minus CDF, and this is the reverse of the CDF. So graph is very much visible to all of you, so that you can see for the different choices of alpha theta, the survival function is uh, basically 0 to 1, basically, for the different values of x. Yes, this is the key results and key properties of proposed distribution. Now, the important part is that any distribution in which we are interested, whether this is discrete, continuous, any distribution, the important part is to compute or is to evaluate the estimator. By using that estimator, we can compute or we can estimate our parameter. So which one is good estimator? And there are maybe more than one estimator. So for which estimator we should go to use to compute or to estimate our parameter? So for that particular reason, there are so many estimators are available, but there are 4 or 5 estimators which is more viable to everyone, because use of these estimators are pretty much easy, and they are they depends only on the CDF and PDF of the probability distribution. So we use several techniques. One of them is maximum likelihood. All of you know, I think, and second one is least square. Third one is weighted least square. Fourth one is Kramer-Rao one Mises. Fifth one is maximum product spacing. These are the estimators we use for estimation purpose in our paper. And the concern regarding these estimation method is that which one is best to estimate in our proposed model. Which one is best? So to judge which one is best to estimate the parameter in our proposed model, one should think about the MSE of the estimated parameter. So we computed the MSE for all these 5 methods, and we judge based on the MSE whether MLE is good or other than the MLE method, which are given in this slide, that LSE, WLSE, CME, and MPSE. Which one is good? We can choose based on the MSE. So to determine the MSE, to compute the estimate of the parameter, it is not so easy. So we did this with the R. We used R. We used R for this purpose, and we found that important result regarding this, that which one is best. So I think this is likelihood function. You see, this is likelihood function for the MLE. So we used R for this purpose to see or to judge which one is best. And in R, we used Monte Carlo simulation. This is one of that old technique, or one of the widely used technique, when the generation of the random variable from the distribution is pretty much easy. One can go with the Monte Carlo simulation. Otherwise, if there are so other techniques to generate the random number, when the distribution is not so much easy to generate the random number, one can go with the Markov chain Monte Carlo, one can go with the MH algorithm, one can go with the Gibbs sampler, any one. It is basically subjective matter. Any researcher can use anything according to their uh, subjectivity or availability uh, of the methods with their PDF and CDF. So we use Monte Carlo simulation and we simulate our result 3000 times. We simulate our result 3000 times, and we generated five samples. Size of sample, first one is 10, then second one is 20, then 30, then 50, then 100. So this means we generate 10 samples first, 3010 samples, and we estimate our parameter. And based on this estimation, what we did, we evaluate MSE. And the same goes with the sample size 50, 20, and 100. And we found a result which is very much important to establish the consistency of the parameter in the estimation process, that MSE should decreases. And we found this exactly same, that MSE decreases as the parameter, as the sample size increases. And we simulate our result 3000 times. So one can simulate this result 5000 times, 10,000 times also. It is basically the uh, a number which any researcher can use, any researcher can choose by their own wisdom. And also it depends on machine, which computer, which laptop you are using. If I am simulating 10,000 result with the old laptop or old computer configuration, then it took, I think, 24 or 15 hours, and machine will get slow also. So, the thing is that I choose 3000, but I did this with the 5000 simulation also, and we found the same result, exactly same, that MSE decreases when the sample size increases. And this the same process we did with the MLE, MSE, MLE, LSE, WLSE, CME, and MPSE. All five estimation techniques which we considered in this paper. We did the same estimation process for the all five methods and determine the MSEs. Now, based on the MSEs, we choose which one is the least, and we say this one is the good estimation method to estimate the parameter in this proposed paper or for the proposed distribution. So MSE, as you can see, third point or of the key simulation result, we mentioned that MLE is the least, having the least MSE among the all other four, WLSE, LSE, CME, MPSE. And in the chronological order, we see that that MLE is the first one, WLSE is the second one, LSE is the third one, CME is the fourth one, and MPSE is the worst method to estimate the parameter for the proposed distribution with the Monte Carlo simulation. So we conclude that MLE is the good one in this estimation process for the proposed distribution. So the same convey through the figure, that as sample size increases, MSE decreases. I think the figure is reverse. Uh, that's why you may confuse, but I think this is sample size increases. This is mistakenly, I think, placed, or some sort of uh, that axis is not here. Now, to validate this model, okay, let's come to the real life data application. The important part is that if we uh, develop anything, any theory we develop, that theory definitely will meet the expectation of the industrial persons, and this is very much applicable. Then only its theory is very much into the for the application purpose. So for this purpose, we used two data sets basically. First data sets basically 30 successive values of Mars precipitation in the that Monopolis St. Paul, demonstrating the model's effectiveness in metallurgic application. So the first data set is basically from metallurgical field, and the second data set is for that COVID-19 cases for 31st May to 30 June from the Italy basically. So we use these two, and now the last part of the proposed distribution of proposed theory is that, oh, okay, one can say how can we convey that this model, yours model is very much good, and why not exponential, gamma, variable, normal, anything else. So for the same purpose, we used AIC, BIC, Archaic Information Criteria, Bayesian Information Criteria, CIC, HQIC values, and KS test or P values. All these six parameters are used to judge whether the model is good or not. And we found that in all these parameter, we found that P value is pretty much high, EIC, BIC is pretty much low, as comparison with the other distributions like exponential, Ridley, Weibull, and some other generalized model of the distribution which is available in the literature, almost for 13 14 distribution which we used for the comparison purpose with the exponentiated x gamma distribution. And if we found that satisfactory result, that it is good, the model is good, we can use. If it aligned with the situation, then we can use only. It is not that we are claiming that this model is the best one among the literature and you can use anywhere. No, if it's aligned with your situation, whether if data is positive skewed, then if hazard rate function, the the shape of hazard rate function is matching with the situation, and then comparison with the other models which is available in the literature, then you can go with, if you find this is suitable, then you can go with this one. For to validate this, I just put it down two pictures, PDF, fitted PDF and ECDF plot for proposed distribution for data set 1, and for proposed distribution data set 2. And in the following table, subsequently, you can see the corresponding methods. We have written the estimates alpha cap, theta cap, and the survival function hazard value of that at that point of time, when let's say t equal to 0.5, 0.1, 1.5. You can give the unit to this t. This may be time, this may be year, this may be month, or this may be some anything. If you, according to your data set, you can give. So for both the data set, we have calculated this survival function, hazard rate function for different estimation methods. And also to picturize the best fit of our model, we have used these ECDF plot for the both the data set. You can see figure 3 and figure 4 also. The conclusion is that the uh, basic conclusion is that the x gamma distribution is more flexible. Sorry, exponentiated x gamma distribution becomes more flexible as compared to the x gamma distribution, because it is generalized form of the x gamma distribution, and it has two parameter. And we developed several properties. One can use moment, or if they can, if they wish to evaluate the mean value of that particular data, they can use this movement. They can generate the movement by using movement generative function, or they can use the conditional movement to evaluate the Lorentz and Boniferini uh, curve, because those are very much important curves whenever we talk about the economics or those something those areas. And the practical implication is that you can apply this anywhere. Just condition is that you should check whether this model is aligned with your data, and then this is the best among the literature. And the uh, future opportunities or future research, uh, we can go with this distribution. We can do with this distribution is that we can use Bayesian framework to estimate the parameter. Then we can go with the censoring, and we can do the multivariate exponentiated XGamma also, and we are doing. And I'm very happy to share you that we are doing. We are in the process to uh, developing these distributions with the some Bayesian framework, censoring framework, and multivariate extension also of the same, and regression models we can also do. So this is the work which and this work is published already in a Statistica journal. This is very much good journal. And uh, apart from this, I'm very happy to share you that my research area is pretty much uh, vast, because I am using SQC for my research purpose, and then probability distribution. Recently, fuzzy distribution, fuzzy theory also explored for this. If any one of you uh, wish to collaborate with me, or do any kind of academic work with me, then you can reach out to me, and I'll share my email ID and WhatsApp number in the text, or sorry, in this platform message. And then, so this is done from my side. Thank you very much for listening me patiently, and anything else from your side, then let me know. Thank you very much.
Thank you, Dr. Harsh. That was a very informative webinar. I have a query in this, like we are having, but actually I am very much curious to know what is the practical significance of using this on any kind of data, because I am very keen to machine learning and advanced graphical deep learning approaches. And if there is some kind of mix and match or the probability of using the exponentiated X gamma distribution to increase the efficiency of machine learning models, then how it is possible, or what
Okay.
is the approach to do that?
See, Mr. Akhilesh, correct?
Sorry.
Okay. So see, in the machine learning model, one can do, see, one can do whatever I am going through right now, because I am teaching machine learning also here. See, the exponentiated
Great.
X gamma distribution is the tool for the parametric inference. Okay, and you can use it. I'm just giving you this some kind of tips for, or not tips exactly, my thoughts on this. We can use this in the machine learning also, because when we see, because most of the machine learning techniques are from the statistics, like principal
Right.
component, k nearest neighbor, machine multiple linear regression, and the discriminant analysis, which is extended to the decision tree, a random forest. So most of the pillar of the machine learning is the parameter statistics. And for the estimation, we can use this as, see, somewhere we apply the normality in the some of the tools of the machine learning. Okay, so we
Mhm.
can apply this to convert this into the normality, then we can apply. So any distribution can convert, or can tend to the normal distribution for n tend to infinity, and that is large sample theory. So by using large sample theory, we can convert, or we can use any kind of transformation to convert this, like say exponentiated transformation. We can have box-Cox transformation to convert any data into the normality. Then in some cases we apply the exponentiated gamma distribution in machine learning also. This is these are my thoughts, because I am teaching machine learning also here. So I found this is very much interesting, because statistics is neglected by everyone, and saying that this is the area is which we don't need. But the pillar of the machine learning is the statistics. Maximum of the
True.
techniques are the from the statistics. Yeah, these are my thoughts. Nothing against any area, nothing against anyone. So you can apply in the machine learning also, by converting this to the normal also, in which we can assume the data from the normal, so that we can have a normality is nothing but, in real life normality is showing that both side are equal, means the symmetry. So positive is also symmetry, negative is also symmetry. So both are. This is somehow we can say we are doing the smart. We are using smart technique to balance the data. So this is we can say greater than zero is let's say 100 observation. Less than zero is also 100 observation. Somehow 199 observation. This is how you can balance by using this exponentiated x gamma with using some transformation technique which is converting into the normality. Then you can use it in machine learning also. You can think about this.
So basically, it can be used at the data pre-processing stage to omit
Yes,
out the outliers from the data and to
yes,
make it
yes,
more
yes.
normalized and orthogonal for machine learning usage.
Sure, sure. Yes, yes. And one more thing, if we can if we use see the support vector machine is nothing but I just observed this the discriminant analysis is available in the statistical literature. Now you see the support vector machine is also we are just determining the line which is or support vectors and support vectors with the two different reasons basically greater than or less than. So in that one also, if you have this kind of approach to let's say see what's going to happen if we convert this into the normal, and then how we approach to the result, then there may be different picture available when you apply this.
All right. So basically, in that case, if we are having this kind of parabolic curve from the for the data, so what threshold we should consider to trim the side lobes?
Uh, uh, but let me give you the this one brief. In the parabolic curve, it is not possible to apply because our
Okay.
model is just is the positive skewed. So whenever you converting this turned out to be normal, it is not going to be
Mhm.
parabolic. So this is that is why I was mentioning that we should very careful because lot of the distribution is available in the literature, and one cannot claim this is the best. So that is why we should conform with our real life situation whether this is positive skewed, whether the hazard function is matching. Then we can go with this distribution and then we can apply the normality transformation to convert this into the normal observation. Then we can apply the machine learning. This is the approach we can go, and this is the basically research area which we can explore because nowadays simply doing probability distribution, statistical quality control, or any area by matter, it does not
Mhm.
solve the purpose. So I am approaching the fuzzy theory also in the same SQC technique, statistical quality control technique, and
Great.
we are also in the process to apply fuzzy in the control chart. And the same, we are also in the process of we are developing some model which idea which I have suggested to you. It may work or not, but we are developing this. If it works, then it's very good.
Great. Great. Thank you. Thank you.
Yes.
So I would like to invite other group, other participants also to share their thoughts and have expertise. Please, if there is,
Hello. Can I ask a few questions?
sure, ma'am. Sure,
Yes.
please.
Yes.
Yeah. Hello, Harsh. This is Dr.
Yes.
Urvashi. So the presentation was very good. Now I have a few questions, right? Firstly, you have done 3,000 simulation for the Monte Carlos,
Yes. Yes.
but
Yes.
the population size, like A and theta variable that you have taken is maximum to the 100.
Yes.
Right. So,
Yes.
why this disparity is there? Like, because you are taking only the sample size till 100 and we are going till 3,000. The
Yes.
other problem is that your, because it is exponential part, right? So, exponential is always skewed,
Yes.
right? So,
Right.
when the data is already skewed, we cannot directly go for the machine learning, or we cannot fuse this concept with the machine learning. Even I
Okay.
heard your conversation with Abhishek regarding the normalization process.
Yes.
So
Yes.
normalization process does not entail in your distribution, right?
Yes.
After
Right.
whatever processing has been done or the data if fits your distribution, then we do normalization. Then again we are playing with the properties of the data set. So like I would
Yes.
like to have your vision at all the 3 points.
Yes. So okay, okay. So first thing that madam you said that Urvashi madam. Okay, you Dr. Urvashi. Sorry. So you said
That's
that
okay. That's okay.
yes, yes, yes. I have chosen the sample size until n equal to 100. As I mentioned that I simulated my data. I generated the sample. I simulated the data with 5,000 simulation also, and with the higher number of sample size. I did this with the 250 sample size with the 5,000 simulation also, and we found out that the results are not exactly same, means that the MSC is decreasing as sample size increases. So to because there are some constraint to journal also, because we should go with the only 5,000 words, some tables. So we restricted ourselves. We just mention only n equal to 10, 20, 30, 50, and 100. I think five sample sizes we mentioned, and with the 3,000 simulation. So one can do any number of simulation with the any number of sample size. This is the first one. Second one is that the point you raised, this is exactly correct. This is positive squid because this is exponentiated one. So that is why I am saying that if you are using this with this some kind of other tool, other problem, if you are not finding it suitable, then you can convert this into the normal, because the normality is everyone everywhere. So you can go with the box scope transformation, logarithmic transform, any kind of transform to convert this first into normal, then you can apply. This is the approach which one can use and I can use also, because if I am unable to find this distribution is fits well to the other distribution, but I have to apply this because this beats every distribution, not every means known distributions like Bevel, Gamma, Lindley, Exponential, inverse Bevel, inverse Lindley. You can go through the paper, you will find that there are 15, 16 distribution which this distribution beated. So one can use this distribution, but the condition is that if you wish to convert this into the norm, and I'll give you the one example. We are basically doing the medical field. We are using medical field data, and how we are using, I am not giving you the name of the person and the name of the college. There are so many thesis comes to me and comes to our group, that to doing the data analysis. And for that we found that the every time it is not possible to model the data with the exponential, gamma, any kind of distribution. And then we can go with this normalization, and this is not just by using myself, I am using normalization, this is with the concern of the
The
co-
normalization, normally we use like it is a generalization, right? When we
yes,
assume
yes,
that the distribution is very uniform, that is how
yes,
we go for the generalization concept. So it
yes,
is a very safer side of playing with the data to get it into the machine learning and without any biasing or any any problem with the skewed data. So that is
yes,
like,
yes,
this is a normal procedure that okay we see. And I think that mathematically also we always assume that when a large size of data is there, that you said that n tends to infinity, you have a
yes,
normal
yes,
distribution. So
yes, yes,
that's always a stand truth, so that has to go ahead, right? So that
yes, yes,
is
correct,
fine, that we
yes,
always do.
yes, yes,
That's fine. Okay.
yes, 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 yes.
So it was nice interacting with you. Great.
Same here, Dr. Vashi, same, yes,
Yeah, thank you.
yes.
Thank you, Dr. Roshi. So, is there any other query to discuss? It's going very into interactive mode and very knowledge sharing session, I must say.
Okay.
All right. So I think, Dr. Harsh, there are no more questions from our participants. And if there would be any query later on, and if I get from them, I would I would like to take your permission to share those queries with you so that we can answer them.
Sure, sure, sure.
And
And
and Scholars Collab is a very open platform, so anyone who would like to collaborate with Dr. Harsh, the profile link is already shared with you in your emails of Dr. Harsh profile, so you can easily connect with him and set up the meetings with him to discuss your research guidance, problems, knowledge session, and whatever you would like to have. And I have observed Dr. Harsh is very open to share his research with everyone. That's very great to have that, Dr. Harsh.
yes, yes.
So
Thank
thank
you
you,
very
Dr. Harsh,
much.
for your time. Thank you, and I would like to again thank you from the behalf of all participants for your session and for your time. Thank you, sir.
Yes, and And I
And
would like to thank to you, Dr. Abhishek, for this opportunity and all the participant who's listening patiently and interactive with some queries also. And thank you very much once again.
thank you, everyone. Thank you,
Thank
Dr.
you.
Harsh.
Thank you. Thank you.
Thank you.
Have a nice day. Good night.
Bye.